Hello everyone. This video is going to be introducing conservative force. And last video we showed that the spring force is a conservative force because the work done by a spring force is independent of path. It only depends on its initial point and final point. And this is video is showing go to another conservative force is gravitational force. And we also demonstrate very simple, this is a very simple proof. This is not very comprehensive, but just to let you know, it's really the work done by the gravitational force is also path independent. Okay, and suppose right now I want to lift the object. Okay, lift the object through path A and path B. So let's calculate the work done by a gravitational force. And in this calculation, it will become like a two-dimensional problem. So we need a little setup also for our coordinate. And then it's an object. Okay. So we set the initial point at the origin. Okay, initial point at the origin here is I. Okay, origin equals A. Then our final point is here. It's x is 5, y is equals 3. And it's A plus A and plus B. And also, yeah, we also let me draw the free body diagram. Right now, yeah, I want to pull force. Whoa, okay. One object. Okay. Schematic one pole. Sorry. Um, hmm. Yeah, same thing. We want to polar object as a constant velocity. Just that we what we set up is spring force. Pull or lifting the object at a constant velocity. Okay. Okay. Lifting the object at a constant velocity. Constant velocity. Yeah, this is because of the same reason. Because we don't want to because we don't want involve any kinetic energy here. Okay, all we want to know right now we only focus on the work done by gravitational force. Okay, we don't want any kinetic energy involving in. Okay, um, so let's calculate the work. Okay, so in this is two-dimensional problem. In this problem, we calculate the work by this formula. It's force is a vector. Okay, because two-dimensional problem, you have to consider a vector issue. Okay, and the displacement is also vectors. Okay, and what's the path A? Okay, path A, its displacement vector is 5i plus 3j. And path B is a little more complicated. Path B, that we will say, path B, the delta R is it's 6 upward and then 5 horizontal and -3 downward. So it will become like this. It's first of all 6 upward and plus minus, sorry, plus 5, I'm sorry, this 6 is J. 6 is J and plus 5I and plus minus, I need to reduce the space. 3. So plus here is -3J. Okay, it has 3 sections. It has 3 sections. Okay, so let's call it B1, B2. Okay, B3. Okay, so let's start a calculation. And our weight is what's the object? What's the mass? The mass is okay. The mass is let's say the mass is the object is 5 kilogram. Okay, 5 kilogram, and G is point downward. Okay, so the force is minus mg. Okay, the gravitational force is minus mg. So be careful. So let's see the path A. What's the work? In path A. What's the work path A in path A? And the force is gravitational force, and it's equal to force times delta R A. And the force is minus mg, so it's minus 5 times 2, and minus 5 times it, and its direction is downward. Okay, that's why it's minus sign, and its unit vector is j, and it's dot, okay, dot 5I plus 3j. Okay, so you are doing a dot product. So we have we multiply the constant first. Multiply the constant, so minus 5 times 9.8 times 5, and j dot r, and plus minus 5 times 9.8 times 3, and j dot j. And if you're familiar with the vector calculation, you see the unit vector, different unit vector. Okay, j and I are 90 degree, and they are perpendicular to each other. And yeah, they are perpendicular to each other. J and I perpendicular to each other. So this is 0. So the whole term here is will become 0. Okay. So finally, you have answers this. Okay. And j dot a unit vector is equal to 1. So your answer is minus 5 times 9.8 times 3 is 3 answers. It's 5 times 9.8 times 3 minus 147. Minus 147. And the unit is joule. In MKS system, we love joule. Okay, that's the work done by the gravitational force is through the path A. And what's the path B? Path B, okay, well, path B has 3 different sections. Okay, path B has 3 different sections. Okay, so let's write down the work done by gravitational force in path B. Okay, is force dot delta R B. And like I said, B has 3 different sections. So I will. I want to look more detail on them. So delta R B1, delta R B2, plus delta R B3. Okay, the gravitational force is minus 5 times 9.8. Yes, negative, don't forget, and it's J, vector J. Okay, doing a dot product. So delta B1, RB1, or delta RB1 is 6J. Delta RB2 is 5, delta RB3 is minus 3J. Okay, so let's see. Okay, let's see. Let's look at term by term. Okay, the first term will be minus 5 times 9.8 times 6, and it's j dot j, j dot j. And the second term is minus 5 times 9.8 times 5, and j dot I. Last term is minus 9.8 times minus 3, and the j dot j. Okay, for unit vector on j dot j, okay, it's 1, and j dot j is 1, okay, and j dot j dot I is perpendicular to each other, so this will be 0, so this whole term will become 0, and j dot j is 1, j dot j here is 1, so we will have this one, okay, so the first term is minus 5 times 9.8 times 6, it's minus 94 and plus 0, and this is plus, okay, 9.83, it's 147, 17. Okay, in overall, the final answer is also 147 minus 147 joule. You see, path A, the gravitational force, the work done by gravitational force through path A and path B, will finally has the same answer, minus 147 joule. And these two pairs, let's see. Okay, these two pairs. Okay, these are two different pairs. The only they share the common is that they have the same initial point and final point. Okay, that's so. This very simple proof just tell you gravitational force is also conservative force, because the work done by gravitational force only take care about the initial position and final position. Anything happening between them, I don't care. Okay, I don't care is initial position and final position. And from doing this the second calculation, you will see this is the work done by a gravitational force. It's it can it's some it can be negative. It also can be positive. Okay, that's in last video I say that's a feature of the non-conservative. Sorry, that's a feature of a conservative force. Sometimes it's negative, sometimes also do positive, and also sometimes it's give you the zero work. Okay, so the force done by a sorry, the work done by a conservative force can be positive, can be negative. So it can release, it also can store. So as a feature, conservative force. So you see elastic force or spring force, gravitational force, it can do positive work and negative work. Okay, it can release energy, also can store energy. Okay, that's a feature conservative force. Okay. And in the next video, I will do an example on the friction force. And friction force, you know, it's path dependent and it's always negative. Okay, doing negative work. Okay. Okay, so here's another example for the conservative force. I hope you understand the difference between the feature of, sorry, I hope you know the feature of conservative force. Okay, so, okay, hope you understand this. It's very simple proof. And hope you understand. Okay, I'll stop the video here. See you. Bye bye.